Hey guys, today we're going to be looking at using the normal distribution, but we're going to be working backwards. We're actually going to go over chapter 5.3, which actually involves us using the z-score table to locate values instead of saying, oh, what's the area under the curve? I'm going to give you the area under the curve. I'm going to tell you find the z-score that corresponds with it. So to get us started, let's say that I have a given area, such as, let's just say that I have an area on my bell curve that is shaded to the left of a given point, such as the one that I have here in blue, and I know that the area of this is 0.7794. So I know the area, but what I don't know is what the z-score is that corresponds to that area. So at this point, I essentially want to answer the question of what is the z-score that represents a cumulative, sorry about my writing there, area of 0.7794. So that's what I actually want to find in this problem. Now, if I take my z-score table, such as the one we have here, as you guys notice, we in the past have been saying, well, if I have a z-score of 2.18, just making something up, I know I can go down the left-hand column to 2.1 and then go across the top to 0.08 because 2.1 and 0.08 add together to give me 2.18. Now, the nice thing with this is I can actually work backwards a little bit and say, well, I know the area, so if it's an area that I can easily find inside of the table, I can work backwards to find the z-score that goes with it. Such as, like I said, in this case, I wanted to find 0.7794. So I'm just going to look in my table for the number closest to 0.7794. Now in this case, I picked this number on purpose because I can just go through and say, oh, hey, look here, 0.7794. That's great. But what z-score does that correspond to? So if you look, we have to go down the left-hand column to 0.7. And when we go across, we go over to the column of 0.07. So I know that if I go down to 0.7 and across to 0.07, they add together to give me 0.77. Which means, if I go back to my problem, the area that corresponds to the z-score that corresponds to the area of 0.7794 is actually the z-score of 0.77. So if I were to just go through and look up 0.77 instead and go the other way, I would find that the area to the left of the z-score of 0.77 is 0.7794. Now you might say, oh, well, that's cool. That's great, Mr. Smith. You're showing me how to read a chart backwards. What point does this have? Well, it comes in handy in some of the problems coming up, which I'll show you in a moment. Before we get there, we sort of have to review percentiles. We learned about percentiles back in chapter 2. When we went over about percentiles, we pretty much said, well, I know if I'm in the 25th percentile, I'm doing better than 25% of everybody. Or if I take a test and I'm in the 90th percentile, I did better than about 90% of the people that took the test, which also means I'm in the top 10%. Now, percentiles are normally denoted by a P with a subscript number, where the number, such as what I have here represented by X, is going to be some number ranging from 0 through 100. So I could have something such as the 25th percentile, or I could have something such as the 90th percentile. And it's written by a capital P and then a number. That number tells you what the percentile is. The normal curve problems actually denote the area to the left. So if I have the 25th percentile, 25th percentile means that I'm finding the area to the left. Oops, let's erase that number right there. I'm finding the area to the left of some z-score where that area is equal to 25%, or 0.2500. If I have a 90th percentile, I can draw a bell curve again. I'm going to find the area to the left of some z-score where that area is equal to 90% or 0.9000. So, percentiles also give me another way of actually finding areas if I understand what's going on with them. So, to give you guys an example, let's say I wanted to find the z-score that corresponds to a percentile of 75. So, I know that I'm going to have some line where the area to the left of that line is going to be equivalent to 75%. And we know that 75% as a decimal is 0.7500. And I want to find the z-score that corresponds to that area. So, excuse me, I'm going to go through and actually pull up my z-score table, which you guys have been familiar with. We've been finding the areas to the left using this table for a while. And I want to find 0.7500 in my table. Now, this is where it gets sort of tricky, because in cases where the numbers fall perfectly on the chart, it's very, very easy. But in this case, it doesn't fall perfect in the chart. If we try to find 0.7500, we're going to see the closest things are 0.7486 and 0.7517. And we know that obviously both of them are not equal to 0.75. 0.75 actually falls right in the middle of those two values. So, what I have to do is I find out that it's going to be either 0.67 or 0.68. And because 0.75 falls between those two values, I'm just going to use 0.675. This is one of those cases where we're going to actually go out to 3 decimal places and just say that because 0.75 falls between 0.67 and 0.68, I'm going to use the number right in the middle. There's actually more accurate ways to get that answer, but if you actually use the graphing calculator to come up with it, it actually falls pretty much right at 0.675. So at this point in time, this is what we're going to do with the chart. I will actually be showing you guys in class how to do this on the graphing calculators. So just sit tight when we actually get there, and you'll be like, Mr. Smith, that's so easy. Why didn't you show it to us before? You weren't ready. So, now, because of this, I know that my z-score of 0.675 corresponds to a percentile of 75%, which means right there, highlighted, is my answer. Now, like I said, this is all fine and dandy, but there's one other piece that we can actually do with this particular section, and it actually introduces a new formula to you guys, which is actually a modified form of the z-score formula. If you guys were to take the z-score formula, z equals x minus mu divided by standard deviation, and solve this for x, you will actually get that formula right there. Now, is that important to know? Not really, but it might make a good bonus question. Now, this formula allows me to take a mean, a standard deviation, and a z-score and actually go through and put them all together to come up with an x value, which is going to be very important for some of these word problems we do. Sorry about that, guys. So, the x value is actually what we're going to be solving for. And my mean and my standard deviation are going to be given to me in the problem. The only thing you guys really need to do is say, well, what is the z-score? The z-score is going to be what you're actually going to be locating on the table. So you're going to be taking all of this stuff, the mean, the z-score, the standard deviation, going to put them all together and you get an x value, which instead of in a problem where I say here is the x value, this problem you're going to find the x value. And that's going to be what the answer to the problem actually is. So, you might say, Mr. Smith, I don't quite understand this. That's okay. Here's an example. Let's say that I decide to be a very, very nice teacher next time on the next quiz and give anyone who scores in the top 10% of the bell curve a homework pass. So basically, you don't have to do your homework. On the recent quiz that was taken, the mean was a 79, and the standard deviation was a 6. What I want to find is what score you would need to get a homework pass, to be in the top 10% on the bell curve. What score do you need to have based off of that mean and standard deviation to get a homework pass? So, I essentially know that I want to be in the top 10%. So, I know that what I want to do is be in the shaded area right here. 0.1000 or 10% as it says in the problem. Now, the only issue with this problem, though, is I'm actually ramping it up a bit. Because all the other problems we did, we actually wanted to find a z-score that actually coincides with the area to the left instead. So what I actually have to do in order to solve this problem, even though I want to find the area to the right, I need to find the area to the left and find the z-score that corresponds with that. And if I know the z-score, I can turn that into an x value. So, if I know that the right-hand side, I want to be in the top 10%, that means I have to do better than 90%. Because if I score better than 90%, obviously I'm in the top 10%. 90% is the same as 0.90000. So I'm going to go to my table. And once again, here it is. I'm going to look up 0.9000. And once again, like I said, in real life, not everything falls right to be neat and perfect. So you guys are going to have to go through and look for 0.9000 on the table. And what you guys notice in this case is it's either 0.8997 or 0.9015. Which one? Which one? Well, in the last example, we went with a number right in the middle because actually the value fell right between those two values. Here, yeah, it falls between those two values, but it's actually really close to the 0.8997. So since it's really, really close to that, I'm actually just going to use that value as the 90%. Once again, like I said, this is not the most accurate way of doing it, but we're just getting an estimate. I'll show you guys the accurate way in the graphing calculator when we actually get back to class. But for now, this is actually the best estimate we can get. And I know that this value of 0.8997 corresponds to 1.28. So I have a z-score of 1.28. Now, I know my z-score is, like I said, 1.28. All I have to do now is actually just plug everything into that test value formula that I gave you guys in the last slide. So I'm going to make some space here for me. I'm going to erase this piece that I don't really need. I know that my formula is x equals the mean plus the z-score times the standard deviation. And I now have all the information that I need. I know that my mean is 79. My z-score that I found was 1.28. I'm going to multiply that by my standard deviation, which was 6. So, if I go through and use a calculator, I end up knowing that 1.28 times 6 is about 7.68. So I take 79 plus 7.68, I get a total of 86.68. Which means, essentially, if I score about an 87% or higher, I'm going to get a free homework pass for that quiz. Now, will Mr. Smith do this for the next test or the next quiz? I can't tell you. What I can tell you is I appreciate you guys putting up with my voice today. As you guys noticed, apparently I am not in school. So please, thank you for trying your best on this. You guys have an assignment that's going to be posted up on the board. In fact, I'm also going to be really nice and actually put it in the video here for you guys at the end too. But like I said, I appreciate you guys doing the best you can. I will be going over this material next time we're in class, as well as having you guys take the quiz that you actually were supposed to take today. So I apologize for that. Just look over your stuff, get ready. Really easy quiz, like I said, multiple choice, 5, 6, 7 questions. That's it. We'll go over the notes. We'll go over some of the homework problems. I'll go over some stuff with the graphing calculators. We'll throw all of that in one day, and we'll get through it. But like I said, for next time, try the best that you guys can with those problems. I appreciate all your work. Have a wonderful rest of the day. I'm off to try to relax.